forgetting it. Cool. Yeah, sorry. Thanks for reminding me because I forgot to record. Anyway, so what as I was saying, so we have actually done, so the two kinds of major problems in machine learning. One is classification and other is regression. So regression is where, so this example of gradient descent, which we did today, or which we did in the last class, is the regression problem, because regression means given some data, we want to fit. So like this is the data, so it becomes a prediction problem in regression, because we want to fit a line, or we want to fit a curve which can explain this data, such that if when someone gives us new data here, it will predict the exact y value for that. So this is the regression problem. Regression is also known as a prediction problem. So in regression, the thing is, you all these are not different features, they're all the same, uh, like one scalar feature, right? So you actually are doing an xy plot. Whereas in classification, given a different observation, we want to see on which side of the boundary it is, and we want to classify them into two different classes. So we will do regression in the. So that regression was the last topic I wanted to cover, because once we'll finish up with all the classification algorithms, then we'll move to regression, and regression will cover it in R. So, so in this case, when you actually fit a line, this line which is fit, the reason why, everything. So the first thing you need to question is, why are we doing anything, right? So why am I fitting this? What is the use of me fitting this line? So in this case, the use of fitting this line is basically, given these observations, when we fit a line which actually can explain this data as close, obviously it doesn't explain it really well, because there is some error, right? The If at all someone says my value is 1550, the actual value is going to be somewhere around like 22,000. But if I'm actually removing this data and just using the line, so 1550 is actually going to give me 20, somewhere around 28,000. So there is some error between 22,000 and 28,000. But given the data, this is the best model. If we take, if we assume that we want to fit a linear model, this is the best line possible, given all the data into account. But then once we have this line, what is this line going to tell us? This line is going to tell us that, in case, like, let's say for example, this is like square feet of apartments and this is their cost, right? So let's say if I take one area in, let's say if I take like the Bay Area, so these are the rates for the apartments or the houses which have been sold. But then once we fit this line, the reason we fit this line is because one main assumption is we're assuming it's a linear relationship. So keeping that relationship assumption apart, the reason we fit this line is because now someone else, let's say if you're working for like Zillow or Redfin, so they tell you like, hey, this is all the data. Now tell me, if a new house comes up in this area, what will be this? Let's say it's 2,200 square feet. What should be the rough estimate? If you actually go to like Redfin or other Zillow, and look up houses, it'll give you a Redfin estimate. So again, I'm just giving a crude example. It's not like they're going to do only this. They're going to run it through like multiple classification and this thing. But the problem they're trying to do, that is a regression problem, because given 2,200, what is the price I should expect for that particular house? So you will be like, hey, I know the data from different points which I got, and I fit a linear model. So linear model need not be the best model. You can fit a polynomial, you can fit a logistic regression problem. There are like multiple regression problems which we will see later on. You can do a polynomial fit, but then I started with the simplest one, which is linear regression. In linear regression, uh, I'm going to basically say that in 2,200 square feet, it is going to basically cost me like, uh, depending on how this line fits, right? So you go and then see what is the y value of the line. So it's going to cost me 33,000 square, 30, I mean, 350K or 330K. And that is the main use of this regression. So for getting that regression line, we have used gradient descent optimization for the values which are a and b, which define the slope and intercept of this line. So having said that, uh, let us go into like the class. So basically, we have seen that decision trees can also. Decision trees, in fact, I've mentioned that in the class, where you can use decision trees also for regression. But instead of taking the mode of the votes, we take the average value of whatever the child nodes are. So they are. So today I'm going to actually solve the bias variance problem which we had using decision trees and basically bagging and boosting methods. So let us quickly recap the bias variance trade-off which we had. I think I covered this uh, in not in super detail, but I've covered it in a little bit of detail in the previous class. But let us revisit this problem and then understand why do we need bagging or why do we need boosting. So bagging, one of the method which we will see in bagging is random forest. So, and then in boosting, we will see adapt boost and gradient descent boosting. So today our goal is to cover, like, firstly understand why is bagging required and why is boosting required. And then we will see uh, and then we'll see how random forest or these boosting algorithms will help remove the bias and improve the and, and improve the quality or improve the accuracy of our results. But before I start this class, I just want to ask you one question just to start, make you think about why are we doing this. So how many of you have seen, like, the show Who Wants to Be a Millionaire? Or at least, do you have any idea of how that show works, like Who Wants to Be a Millionaire?
I do.
Okay, so in Who Wants to Be a Millionaire, basically, I mean, at least like I've seen the Indian version of it. It is called Kaun Banega Crorepati. Like there are like lifelines, right? So basically, there is a phone a friend. There is 50-50. There is audience poll. I forget what the fourth one is. Anyway, so there were four lifelines as far as I remember, or maybe there were only three. Maybe my bad. Maybe there are only three lifelines. So if you actually look at the history of the show, can you guess which option or gave like the best results to the contestants? Like which lifeline was mostly successful?
The audience poll or something.
Yeah. So if you take the whole all the segments, and if you actually see which one is successful, the audience poll was the most successful of all the three options. Why do you think that is the case? Why is audience poll more successful than phone a friend or basically using 50-50 or something like that?
Because you have more people agreeing on one answer than if you phone.
Exactly. And then, so the bagging boosting techniques are kind of similar to that. So basically, when you actually have a problem to solve, yes, you might end up with a model. Like there might be some dumb people in the audience, or I shouldn't say dumb, but there might be people who don't know the answer to your question. But when you actually take an overall aggregation of the majority of people, and because they actually have a percentage in between four options, it it almost around like 80% of the time they end up giving the correct answer, because you have in the audience, you have people who are like come from like uh, various backgrounds, because it's not like the audience is only good at answering questions on movies or this thing. They even answer questions on political science. They answer questions on geography and stuff, because given like 100 people, there you'll at least find like 20-30 people who know the answer to that. But then when and the other 70% or other 70%, they will be divided equally in the other options. So the major chunk will still remain 20-30%, which will be your highest voting technique. So today what we are going to see is a similar approach in machine learning, which is called bagging. So first and foremost, why do we need bagging? So I'll give you like before I go into like bias variance criteria, let me just tell you what bagging is. So bagging is basically a procedure where you will, instead of relying on one classification algorithm, you will take the training data set and then create like multiple number of classification algorithms. You first take the training set and create from that training set, you will create D1, D2, D3, you will create training data sets. I'll tell you how we divide them. I'll tell you what with replacement, without replacement is. But the idea is kind of similar to like the audience pool. So you have one training data set. Instead of taking one decision tree, I'm going to create like n number of decision trees. Each decision tree will work on different data, and each decision tree can have different parameters. So I'll create different number of decision trees, and I'll get their classification results out, and then I will pool all those things and take the maximum, like whichever decision trees. Let's say if like create I divided them into 20 data sets, and let's say the highest number of, or the highest classification results I got were by combining like 10 of them. So we combine them and then we give it. So it's kind of like the audience poll sort of a thing. Now, the question you ask is, why do you think this is going to be better? So it is going to be better because the same reason why we think like audience poll is generally better in Who Wants to Be a Millionaire. First and foremost, the reason why we do this, we have to understand it. Again, go back to this bias variance trade-off criteria, which we actually spoke about it a few classes back. And maybe right now you don't understand the right now you might not understand the seriousness of it, but when you actually start working on these problems, data science problem, you will see that the bias and variance trade-off is a huge I mean will you can actually improve your results by around 8 to 9% more if you can tackle the bias variance trade-off problem really well. So let's the term, I don't want to like use the bias and variance because it it is, you have to understand what bias is, you have to understand what variance is, but a simpler way of using bias variance thing is overfitting and underfitting. So let's look at this example. Can everyone of you see my screen, right? I think I'm sharing my
Yeah,
screen.
we can
You
see.
can see, right? So basically, let's look at the overfitting problem in the classification example, right? When you try to classify between two classes, so let's say all the blues are class 1 and all the reds are class 2. 1 and this is 2. So before that, I know I repeat this every class, every this thing. What is each blue dot and what is each red dot? So how do we get to these dots?
That is your training data, right?
It is training data, but what does each dot represent?
Like either class 1 or class 2.
That is correct. But so I think maybe I was asking for a more general answer. So let's say we have observations, right? So let's say we have like patient 1, patient 2. Each dot represents the features. So we have, let's say we have 5 features. So the 5 features can be like blood cholesterol levels, bilirubin levels, some other levels. So each of these 5 features, when you plot them on a 5-dimensional plane, they become a dot. So each of these dot represent features. So from how do we go from data to this thing is like you first take the features, and the number of features you have, you plot them in an n-dimensional plane, equal to the number of features you have. Then each of them will become a point. So I know I repeat this every single time, but just it's good to know, because how do we get these points? These points are nothing but features, and these points are also nothing but the training data set, as you mentioned, Deepika. It is the training data set, and you basically get them from features. Each of the dot represents feature from that particular class. So the blue dot here represents, let's say if you are classifying whether the patient has disease or does not have disease. The blue dots are the ones which patient have diseases, and the red dots are the ones which patient does not have diseases. And each of the dot here represents that feature. So in the machine learning problem, the main thing which we are trying to solve is to find the equation of the boundary. So how do we classify the boundary? So now, like I think even in the last class when I mentioned, right? So the problem of overfitting is this green line. So this is overfitting. Why do we call it overfitting? It's because it is actually drawing the boundary so very stringently that it is actually having a training error of like 0. The training error is 0%. The training accuracy is 100%. So that is really good. Everyone will think that, oh, you know what, this is so nice because In your training data set, you are actually learning the data so well that not even one of them is misclassified. But the thing is, you shouldn't do that. If you do that, that means your data is learning the training data. So, and it is also basically not. What is the harm in learning training data so well? The harm in learning training data so well is the fact that we can never get training data which can accurately represent what your test data is. Sometimes your test data can lie anywhere within the boundary. Let's say if we actually learn it this well, and suddenly there is a blue there is a blue dot here. Because of this one point, you will actually misclassify those blue dots. Let's say there are blue dots here, right? Because of this one point which you learned really well, you'll actually have a more test error, because if the blue dots lie here, it was not a generic boundary, but it is only learned to an extent where the data is precisely mapped. But the thing is, so this is what is the bias variance trade-off. But the thing is, if you actually look at it, there is a black line here. So this is our optimal line. The reason for that is because when you actually have test data, it it can be completely, I mean, it not completely, it will still have the characteristics of the training data, but it is more generalized. So one way of solving this bias variance trade-off is by taking a lot of training data. So if you take a lot of training data, which, because the more the training data it is there, the more general you try to learn it, or to stop this learning of this algorithm prior to overfitting. So you don't learn it to an extent where it completely overfits it, but you can stop it prior to overfitting. So these are the two things which we talked about. But then there is this other concept called bagging. So what bagging does is, but before I go into bagging, let me just quickly overview this thing. So bias. So what is bias? Bias is how much on an average the predicted values are different from the actual values. So in this case, basically the bias for on the training data set for this green line is almost equal to zero, because everything is classified correctly. So that is the bias. Bias is basically how much on an average the predicted values are different from the actual values. And variance is how different the predictions of the model, how different will the predictions of a model be at the same point if different samples are taken from the population. So variance is basically, once you have this model, if I take if I take this new data set, right, how much different or how much is the classification error you get once you actually set this model. So variance is basically an estimate of your test error, and then bias is an estimate of your training error. So that's why when you actually go down and see, so when do you have high variance? When your training error is less and your test error is higher. And when do you have high bias? Your bias will be high when your training data is higher, right? So if you look at this graph, I think this graph will probably explain this thing better. So your bias will is a representation of how your training error is, right? So if you have a low bias, that means that your data is like overfit, maybe bias close to zero. And your variance is a measure of your test error. So basically, if you act, so that's why there is an optimal point at which we stop our training. So any questions on bias and variance trade-offs? Because I have some examples here, like, okay, if your training error is basically, is if your training error is low, what is low? Is your bias low, or your variance?
Bias.
The bias is low. So basically, that's what is the bias variance trade-off is. So to solve this problem, what we do is something called as bagging and boosting. So boosting and bagging are basically techniques for which you can avoid the error which you get from training and this thing. But the idea behind that is also the same. So what we do in bagging and boosting is the following. So there's something called as ensemble methods. Ensemble methods are the reason for solving the bias variance trade-off. Or to reduce the error which you get from overfitting the training data. So the term ensemble means multiple. So ensemble methods means that when you have a technique in which that combines the predictions from multiple machine learning algorithms to make more accurate predictions than any individual model. So instead of using one similar model, we use like multiple of them. Let's say we have n models, right? We use n models to actually get the results, and then we combine the n models. And these n models are not using the same training data set. We will create like subsets of the data set. So we'll take one data set. Let's say we have like 10 samples here, 1, 2, 3, 4, or let's say we have 100 samples here. So from this 100 samples, we will create 10 subsets or 10 different algorithms. And for each of them, let's say we won't take all the 100 into account. What we will do is we will only take, like, let's say we take only 30 features or 30 observations. So we take 30 observations at random, and we do that 10 times. And each of these 30 observations will be given to 10 different algorithms. And then after we get the results of the 10 different algorithms, we combine those results together. The reason being that we don't want to use entire training data set into one algorithm. So let me go back to that example where that overfitting was. So here, now we have, this is our training data set, right? We have like a lot of samples. So here we might take this one, this one, this one. So we're doing it random. This one, this one, this one. We'll train one model with these samples. Another sample, we'll take this one, this one, this one. So all of them are taken at random. And before we go into that, there is one concept called with replacement and without replacement. You might have heard about this in probability. So with replacement means that in these 100 observations, let's say if I pick 30, right? So I pick 30. For the next set, the new 30 algorithms which I need to pick, what I'll do is I'll put these features back into the bag and then again choose 30. So this is called with replacement. That means that you already chose 30. So the next time when you choose, so now there are only 70, right? You have to choose from 70, right? This is without replacement. But when you put this 30 back into this, next time also you're choosing from 100. So if you're doing this, this is without replacement. If you're doing this, it's called with replacement. So most of these bagging techniques are always with replacement. The reason for that is it is okay to repeat the data, but the randomness in our selection of the data set takes care of the fact that we won't get the same data again and again. The reason is because then if you don't do it without, let's say if you do it without replacement, you might get, let's say for example, you might get all these data sets into one. So now if you remove this whole chunk away for the new set, then basically it's bad, right? Then you'll only learn one part of the curve. You don't want to do that. You want to learn this curve from different algorithms and then combine them to get a smooth curve back. So you understand why we want to do it with replacement. The reason being, if you do it without replacement, let's say if I somehow get these things in one first iteration, right? The next one, if these are gone, then I'll only get this. Then I'll only get this. So we don't want to learn. So we are not trying to learn this in chunk, this in chunk, this in chunk, this in chunk. We want to learn everything together. So we want to learn the first model with every like, with the whole distribution together. The second model also will be the whole distribution together. Third model also will try to get aspects from the whole distribution together, and then we'll combine them to get like one distribution. So this concept is called bagging. So the reason is, if you look at it, we are taking a bag and putting 10, like in these 100 observations, we are putting 30 of them in this bag, and then we are training one model. And now we will take all this observation, put it back here, and get one more bag and take another 30 observations from here. We'll train one model. Put this back again, another 30 observations, and we'll train another model. So this concept is called bagging. The reason we are doing bagging is to avoid this overfitting problem, or to actually understand how like again, two things. One, once we do this bagging, there's a different algorithm which we use here. So we have one data set of 100 points, but we create 30 times. We can even create like 200 times also, because we are doing it with replacement, right? You'll, every time you get one, you're going to like predict one model. So we are, you, let's say we are taking 10 classifiers. You can take 200 classifiers, you can take 300 classifiers. There is no limit on how many you can take. It depends on your processing time. The more classifiers you have, the more time it takes to classify.
And now I
But
have a question about
yes,
this. So, but like, if there's no limit to the number of bags that you can have, or the number of times that you could try to fit the model,
yes,
uh, then what's stopping people from using? Like, wouldn't you get very, very accurate results if you did this a million times?
no. The reason is there'll be an overfitting happening there also. So if you're
So
doing
then,
it a
so then
million
here
times,
also there's like an optimal amount.
there is an optimal amount. So generally, there are two things which stop people from doing it million times. Is one is the time, right? Because if you have like 2 million classifiers, the time taken to train million classifiers is a long time. Second is computational efficiency. And also there is an optimal thing for this thing as well, because the problem we are trying to solve is overfitting. But if you're actually learning models for a million times, then you will again result in that overfitting model. So every model, basically when you combine them, you shouldn't exceed to such an extent that you overfit with those, with the bagging too. That's why bagging is generally limited to like, depending on your data size, we generally limit it to around like I think a good percentage would be like 20 or 30% of your data size. Like let's say if you have 100 samples, we generally train like 30 models or like 20 models with the thing. That's the max. You don't go beyond. But ideally, you can go up to million, because we are doing it with replacement. So you, every time you choose a random set of 30, and you can always train that. But there are different. You shouldn't overfit even in like the bagging model. Is that clear? Because the more million times you learn, you will, each classifier again when you combine the results, the idea, so it's like this, right? The idea behind that is basically to divide the data sets and to see how, like let's say if we, by mistake, right, like if I came up with one bad classifier, the and then you won't be restricted to this classifier itself. Now when you're doing this 30 times thing, you might get different classifiers which are good. So, and then when you combine all of them together, you basically and you do the voting, you basically end up with like what results you get from good classification results and stuff. The similar idea to like audience score. So if you take like audience, so basically that's the whole concept of this, right? So there might be people who don't have, so think of each member of the audience as one classifier you had. So you might actually come up with a bad training model depending on some data which you must have gotten and this thing. But when you do them multiple number of times with different kinds of like in this case, I'll take decision trees as an example. So each decision tree is different. So one decision tree you can use depth of two, other decision tree you can use Gini index, other, or else you can use entropy. So there are like different ways you can come up with this thing, because there is no, only the results will tell you, right? So this is a guess. Depending on the data distribution, you first guessed which one to use, but then when the data models become more and more complex, you generally go with a bag of decision trees, and that's why it's called a random forest, because a forest consists of trees, right? If you take a forest, it consists of a lot of trees. The reason it is random is because you're picking these observations at random, and then you create something called as a random forest. Is that clear? So what is bagging and why do we do bagging? And an example of bagging is random forest. Random forests are the ones in which you actually can train multiple number of classifiers, and then you can see. So, and also you will see that the more times you, like after a certain extent, the results will kind of uh, like it will kind of converge. Like if you have like uh, so let's say somewhere around 200 to 250, you the results won't change much. But if you again go into like 1000 2000, you will again start overfitting the models. So that's one of the reasons why we do bagging, and it tries to generally improve the accuracy of your algorithms much better.
So each feature is a tree in random forest.
Each feature, no. So each tree is, no, I didn't get your question. So each feature is
Like
a tree.
each dot on this model will be uh, considered a tree, right? Because we're placing random trees into a bag.
No. So okay, I think maybe there's some confusion here. So you basically, so these are, let's say these are 100 observations, right? So first thing what we do here is we take 30 observations from this. So maybe you pick this feature, this feature, this feature randomly, this feature, this feature, this feature, this feature, this feature, this feature. And on these 30 features, you do a decision tree. And this decision tree, so it's not on every feature. You pick 30 features, right? So you have a data set of 100 observations, and you train your decision tree only on these 30 features. Or not features, sorry, 30 observations. So these are all observations, they are not features. Each observation consists of like 5 features, maybe like 6 features and stuff. So you can basically take like 30 observations and then do it. There is another decision tree in which you don't pick all the observations. You can, let's say if there are 10 features, you can only pick 5 features here. So there are two ways you can actually do bagging. One, you can do it on the number of observations you have. Second is you can also do it on different features you have. So you can take, like, instead of taking 5 features altogether, you can take only 3 features and then do your decision tree. But the decision tree depends on the number of observations. Is that clear? Or so
Yeah,
let me
so that's
understand. Let me understand you. Why did you feel like each of them will have a decision tree? It won't, right? A
no.
decision tree is.
I wasn't saying each one will have a decision tree. I'm saying so in that 30 that you pick,
Uh-huh.
those 30 will be in one bag, right? Or like they'll be one forest.
Yes.
Right. So that's what I'm saying. So I'm saying then each dot is considered to be a tree in the forest.
No, no. So these dots are observations, right?
Yeah. So each observation is a tree in a forest, right?
No.
See, that's
So,
what I'm not understanding.
okay. So, firstly, you have a decision tree, right? What,
Yeah.
what, okay, forget about like 30 or 40. I have 100 observations. I have a decision tree. So, what is the decision tree doing to these 100 observations? It is trying to draw some lines, right? For it to like classify this into two data sets.
Yeah.
So, that is one tree. Now I'm saying I'll take the same observations and create another model in which I change the type of the tree. My decision tree now, instead of using Gini index, I'll use entropy. So this is another tree which takes in the same observation. It might come up with a different decision boundary. It might come up with a boundary which is like this. This can come up with a different decision boundary. So this is just observations, or these are our feature, our training data set. A random forest here is meaning that I took decision tree 1, I'm taking decision tree 2, I'm taking decision tree 3. It is the random forest algorithm is a combination of these decision trees. This will give one output, this will give one output, this will give one output. Then we will aggregate the outputs of all the three and then decide on what classifier we want to get. So each dot is not a tree here. Each dot is just an observation. Each tree will have a decision boundary for the observations. So the first decision tree can have a boundary which is like this. Second decision tree can have a boundary which is like this. The third decision tree can have a boundary which is like this. And ultimately, we combine the results of all the decision trees into one. I think maybe to understand or to answer your question, I'll let you okay, let's take what you're taking. Let's think what you're asking is correct, right? So you are saying that each dot here is a decision tree. Like, how do you explain that? Like, if this dot is one decision tree, what is it doing?
I didn't mean it as like I didn't mean it as a decision tree. I just meant it as in like one entity of a bigger like environment. Like one tree is part of one forest, right? How I thought this was working is you pick 30 different random points, random dots, and each one of those are considered like quote unquote trees. And then you do a decision tree on those 30.
No. So I think that's where the decision, the decision tree works on. There's only one decision tree for 30 observations.
Oh, that's what I'm saying too.
Okay.
I'm also saying that. So I'm saying, so you do that one decision tree on 30 observations and you get an output boundary.
Yes.
And so then you pick another 30 points on the graph and you do a decision tree on those. And so you keep doing that until you used up all the training data. And then wherever all those points intersect, that's like your model.
Yes, that's correct. So maybe I think I got confused when you said each dot is so it's not each
Yeah.
dot.
So when I meant to say that, you were using the analogy of forest, right? So like I could have said something like, like one like I meant to say one small entity, like one human in the world or something like that. Like if you consider the bag as the world, then each.
Okay. Yeah. No, I think I got confused with this example, which.
Yeah.
Okay, I understand what you're saying, right? Yeah, like in case of the audience poll example, each member of the audience is like one decision tree for you.
It is like one tree, yeah.
Is like one tree, but this particular graph is the observations and stuff like that.
Right.
Maybe it'll be a little bit more clear when I actually talk about decision tree in general. So anyway, I have some examples of what high variance and high bias is. When you have high variance and high bias, it means that your training error is large and your test error is also large. So I have some examples which actually have. So we want to go for a low variance and low bias, where both of them are. Uh, low bias means that you might be entering into the region of overfitting. So you want to actually have an optimal model. So, but anyway, I think that is pretty clear as to. But here is the thing: techniques for reducing bias. Bias is also like the training error. So you can increase your model size. That means you can actually increase the number of observations you can train on. Modify the input features based on the insights from error analysis. So when you actually take errors, you can see that which of the features are actually causing more error, and you can modify what your input features are. You can modify your model architecture. You can reduce or eliminate. So regular, okay, I think the term regularization is also used quite a bit in machine learning. The term regularization means generalization. So the concept of regularizing the data is the concept of having a general boundary. So this is a regularized boundary. This is non-regularized boundary, because this is like it's not a generic. It's overfit to the data. So you can reduce the bias by actually. So one way to handle low bias is by actually regularization. So that you don't run into the problem of overfitting the data. And another way of reducing variance is you actually have like more training data, early stopping. You decrease like the model size. Again, modifying architecture is this thing. Feature selection also. So one other way to create your decision trees are, if you, let's say I told the decision tree on observations, right? Let's say I said you have 100 observations. You can also create a random forest based on the features. Let's say if you have 10 features, right? You can instead of taking all the 10 features, what you can do is you can take 5 features, put them back again, take another 5 features, put them back, another take 5. So you can either replace the observations or you can replace the features. So you can do the bagging models based on both of them. I think when we do an example, it will become more clear. But any questions so far on like what bagging is and like how we are handling the bias variance trade-off, and why do we need an ensemble method?
No, what was the question?
The question is this clear? Like, why do we even go for ensemble methods?
Oh
Uh,
no.
or like any questions on because now we will look at bagging a little bit more detail, and then we will see random forests, and then
Yeah,
we will do an example.
could you explain the ensemble method? Like I didn't understand how this fit into everything.
Yeah. So also I have a question. So is an ensemble method the process of bagging? Little confused what it is. So bagging is one of the ensemble method. Ensemble, the word ensemble itself means multiple methods. So you basically, so ensemble method is basically a technique that combines the predictions of multiple machine learning algorithms and then creates a more accurate model than any individual model. So that is an ensemble. So an ensemble method, the ensemble method is the process of actually creating multiple such algorithms and combining them. Bagging is one example. So bagging is one example of ensemble thing, because bagging also actually puts some features into bags and then gives an output of that. Puts another features into bags and puts gives an output for that. So bagging is one of the ensemble methods. But the reason why we actually require ensemble methods is because we want to create a model, multiple models, such that which can give you a much accurate result than any individual model. So this will give you better accuracy. It will become more stable and impart a super boost to. I'll talk about like how boosting is also going to affect this particular model. But this is basically what ensemble methods are, and bagging is one such example of that. Yeah, so bagging is an example of an ensemble method. Like so. And so the result of like, so if we use decision trees in bagging, it's called random forest, because a forest consists of different trees. So so ensemble method, bagging, if your algorithm is decision trees, then it is called a random forest. So this is the whole structure of how it actually works. There's something called as a bootstrap method also. So bootstrap method is a powerful statistical method for estimating quantity of the data. Let's assume you have 100 samples. We would like to estimate the mean of the sample. Then we calculate the mean. And then as our sample size is small, our mean has some error. So if we can improve the estimate of our mean, it's called a bootstrap method. So bootstrapping is another thing. So bagging and bootstrapping are two different ensemble methods. So basically, in bootstrapping, what we do is we actually uh, start from our sample, and then we try to estimate, like reduce the mean of that particular observations. So we don't cover much of bootstrapping in this lecture. We'll cover mostly like the bagging this thing, but we'll talk of what bootstrapping is. So bootstrapping is basically create 1,000 subsamples of our data set with replacement. Okay, sorry. I think this is bootstrapping is one of the methods which we use in ensemble. So I'm sorry, it's not a different method, but bootstrapping is the method which I was talking about, where you take, like in your observations, right? You actually take some of them and then create your model. That's basically called the bootstrapping process. But then the reason how we do that is basically uh, by taking the mean of the observations. So let's go through this thing. So let's say create many random subsamples from our data set with replacement. So did everyone understand what with replacement means? With replacement means that, let's say if you have 100 and you pick like 10 observations, for the next time when you want to pick another 10 observations, you put these things back into uh, your original sample and pick them again. So that is basically uh, called with replacement. So in bootstrapping, you calculate the mean of each subsample. The average, calculate the average of all the collected ones. We use that for an estimated mean. Question: is a random forest a type of greedy algorithm? Yes. we can consider random forest as a type of greedy algorithm too. So for example, let's take we take three resamplings who got the mean as 2.3, 4, and 3, and the average of this thing is called is actually 3.37, 3.369. This process can be used to estimate other quantities like standard deviations and uh, other metrics in machine learning algorithms. So the concept of bootstrapping means that, so this will give you, so let's take, if you, let's say you have 100 samples, right? And let's say we took like 10 of them. You first calculate the mean of these 10 samples. Then you actually create another sample, you take the mean of that. You take another sample, you calculate the mean of the other one. So in all these means, if you take the average of these means, you will get a distribution of how your data collection looks like. So you can actually estimate how good your how good your ensemble methods work based on these metrics, which are the average, standard deviations, and stuff like that of this thing. So let's look at so I was actually talking about bagging, right? So bagging is, why do we use bagging? We use bagging to reduce the variance of algorithms which have high variance. So high variance meaning high test error. An algorithm that has high variance, uh, basically one of the algorithms which has high variance is decision trees. I think one of you has asked this question because, you know, decision trees actually go back to an extent where you go into sub leaves and then you divide those things further, you divide those things further. So so that's why I actually talked about a concept called pruning. Pruning means we don't go all the way to the leaf nodes, but we stop the tree at one point. But in case if you don't stop, if you don't use pruning, one of the algorithms which has high variance is basically decision trees, because of the fact that you're going to drill down to an extent. If you actually create a complete decision tree, you drill down to an extent where you subcategorize uh, each leaf feature, each leaf node according to the feature set which you have, right? So they are susceptible for overfitting problems. So the decision trees are sensitive to the specific data on which they are trained. If the training data is changed, that is, the resulting decision tree can be quite different. This in turn can lead to different prediction. So this is pretty straightforward, right? Like if you actually give it the training data, if you change the training data, because decision tree is based on the features. So how does a decision tree work? We select these features based on the Gini index and entropy, and variance. We saw 4 methods last time when we did decision trees, in which using which you do the split. So we take feature 1 and then we split. If we take and then feature uh, 3 and then we split using that. We take another feature and we split using that. Now let's say if we give a completely different training sample to this, they will fall into different buckets, because this training sample might not adhere to the same set of features which the previous training samples went through, right? So that's why it is very susceptible to the data in which they are trained on. So bagging is an application of bootstrap procedure due to high variance, which for any machine learning algorithm called decision tree. So anything in which the algorithm is a decision tree, the bagging algorithm is called a random forest. So here is an overall example of how this thing works. You actually take one training data set sample, and then you create like n or like t data samples from this training data set using replacement. So you basically take, let's say if you have 100 here, you can divide them into, let's say you can do to 30, and then this will have 30, this will have 30. You can get like 10 such samples, because you're putting them back again, putting them back again, taking. So now you have 10 data models. For each of them, I will use multiple classifiers. So in the first case, I'll probably use a decision tree with depth 3. In the other case, I'll use another decision tree with depth 2. In another case, I'll use Gini index to split it. So you can create multiple classification algorithms for each training data set, and you take the output of each classifier and then you combine them. So this is what is the classic example of how like how these bagging algorithms like random forests work. So creating multiple data set. So sampling is done with replacement on the original data set and new data sets are found. The new data set can have fraction of rows in general, which are generally the hyperparameters on this. So basically the new data set like this 30 is basically a hyperparameter, right? Like how much data in your current data do you want in your new data set? So uh, uh, that is basically an input parameter to your bagging algorithm. So, and then you build multiple classifiers. Each classifier is built on one data set. Generally, the same classifier is modeled on each data set and predictions are made. So you actually create like 10 of them, right? So once you make a classifier for this will be the classifier for this thing. So you model one classifier for each training data set. So if you want, you can, because there's no point in actually doing the same classifier for everything. So you try to change the hyperparameters for each classifier algorithm. You have classifier 1, classifier 2, classifier 3, and then each of them will actually give you an output. So combine the classifier. The predictions of all the classifier are combined using the mean, median, mode value depending on the problem at hand. So you sometimes, if you want to do a regression classifier, you use the mean. If you want to do a classification classifier, you use the mode. So depending on whether you're doing classification or regression, you will either take the mean or the mode of the classification output. The combined values are generally more robust than single model. So for example, right, here, let's take if you have a purchase value of a property, and then they are like basically different features. One is the carpet area of that property, other is number of bedrooms, then you have average income of the people in that locality, the lifespan of the property, which is how old it is, whether it's commercial or residential, how much time does it take to go to school from there. Let's say we have a total of 10,000 examples and we decided to create 30 data sets of training 30 individual classifiers, with each taking 7,000 samples out of 10,000. So from 10,000 you took 7,000, you created one class. Now you put back the 7,000 again, you take 7,000 again. So this time it will try to, we're doing this randomly, so it might not be the same data as what we have done, and we are doing it for 30 different classifiers. So each data set, 7,000 out of 10,000 are selected at random. That's the key there. So now each individual train is grown. So now you don't do pruning, because now anyway you are actually selecting subsamples of these things, right? So you don't do pruning in each of these individual classifiers. So each individual decision tree are grown deep, and the trees are not pruned. These trees will have both high variance and low bias. The only parameters when a decision tree is the number of samples, and hence the number of trees to include. So basically, we are saying the two things in the bagging thing is what? So you have like 100 features. So what are the two parameters for the bagging algorithm? So when you're doing bagging, what are the two features which we will use? Let's say I have 10,000 observations. What do I need to decide here to go ahead?
Number in each bag.
First one is number in each bag. And anything else?
Your multiple classifiers.
Yes, number of classifiers. So number of classifiers and number in each bag. So those are the only two things which we need to decide. We won't then prune. Then we will fit. We don't care if we overfit the results in each classifier, because ultimately we're going to combine them together. So one reason why we won't do it for like a lot of times is the time constraint. So ideally, you can actually still go and do it like a million times, which will actually like create different things. But after a certain point, they'll kind of like narrow down to one this thing. So we don't generally do. Main thing is because I think I said earlier that we will overfit even if we do this thing. By what I meant by that is we will come up with the same smooth line every single time if we do it for a lot of time. But the first constraint which we have is basically the time. You cannot wait for a million classifiers to train and then give you the results. Ideally, the higher the number, it's better. But one thing is, the higher the number, it'll kind of if you it'll kind of result in the same smooth line again and again and again and again. So we don't do that with certain things, but you can actually try it. One thing you can do is you can create a plot with the number of classifiers you have and the number of samples you have. Let's say, not even that, let's say you have 7,000 samples, and then you have these classifiers in your graph, and then plot error versus that. So you will see that the more times it goes, and then it kind of flattens at some point. So ideally you can do it for like 1 million also, but this is like useless after some time, because one, it flattens, and second, also the thing is your time. So you can't waste time in basically this thing. So number of models is always better, are always better, or may give similar performance than lower. So as I said, right, if you keep on increasing, they might give you similar. After a certain point, they might actually end up giving you the same results. So the variance, so now the main reason is, this is the reason. So the variance of the combined prediction is reduced to 1 by n, where n is basically the variance which we got from each individual classifier. So now if we had high variance in each of them, because we are combining the results by taking the average of all of them, we are reducing the variance to 1 by n. So that's why we will have a lesser variance. So now let's, so before I go into random forest, any questions so far? Do you understand why we use bagging, why we need to classify them, what are we changing? The reason why we are changing is because of the variance and stuff. Any concept you want me to go over again? Deepika, do you have any questions on this? Hey, can you guys hear me?
We can hear you now.
Oh, okay. Because we just lost power. I don't know why.
Okay, strange.
It's very strange. Okay, there's some class. So any questions on like what ensemble methods are, what bagging is, like why do we train random forests and stuff? Can you guys still hear me?
Yeah, we can hear you.
Okay, cool. So no questions, right?
No question.
Okay, because this is like this is sometimes we use bagging and boosting for. So the first thing is basically we decide on the algorithm first, and then after we like train our algorithm on using one such model, then we go into bagging and boosting later on. So bagging and boosting comes at the second step of like, but first thing is we decide which algorithm we want to use. And then the next step is improve. If you want to improve the accuracy further, that's when we use uh, the bagging and boosting. Because in this case, we first need to decide on what classifier we want to use, right? And then we can actually then combine them into different ones. So random forest is one such technique. So in random forest, what happens is you actually take a group of weak models and then combine them into one powerful model. So each decision tree need not actually give you like the best result, but then you combine them into a random forest. You create a random forest, and when you combine each decision tree output, combine them into one. That's when you will get uh, a better result. So the capability of performing, it can do both regression algorithms and it can do both classification algorithms. Then it can actually use dimensionality reduction methods too. So one thing I said right now is the observations, right? We can actually take, when we have 100 observations, we can take 30, classify them. We can take another 30 and classify them. Another thing which it can do is in each observation, let's say we have 10 features. So we need not take all the 10 features. We can take like, let's say we take like 5 features in one and the other 6 features in another one, and then 7 features in another one. So that will actually use dimensionality reduction. So these are the dimensions of that feature set. So we can use lesser dimensions also and train. So the idea again is basically if you take like enough number of samples, we will basically enough number of classifiers, it will average out the variance from each classifier and give you a classification which has lesser variance. So let's so decision trees, we actually say they're greedy, right? Because they choose which variable to split on greedily, which minimizes the error. Even in bagging, we actually use the same technique. So random forests are an improvement over bag decision trees because each of them you can actually change. So if you look at this thing, right? Let me show you. Let me show you the code here. So basically, the code is pretty straightforward for a random forest classifier. So what you do in that is, again, you use a test train split of what algorithm you want. You create a random forest classifier, and then you fit the forest classifier, and then you actually print out the training accuracy in the thing. So the model is pretty simple. You just create something called as a random forest classifier, and it will basically create different decision trees for you, and then it will basically try to run these on different classifiers and then combine them together. So the code for this is relatively straightforward. So what we do is we just create a test train. So most algorithms, since we are not changing like the implementations from what the sklearn does, we basically just uh, one thing which we need to do here is basically use the ensemble method, sklearn ensemble, and then we import the random forest classifier, and then that will basically take into account like each decision tree and then combine them together. So in your previous models, right, you have used Indian liver patients, this thing, can you just quickly change this into a random forest classifier and see what your accuracy output is? So even like, I think it's the same model, right? We first take the data, we split the data into test and train, and then we basically create a model for the random forest classifier, and then we predict it.
Okay, will do. I can start coding now, right?
Yeah, just start coding now, because I think with an example of like how the random, you can see like, or you can just take the data which we have used for decision trees. I think we have used Indian liver patients there.
you can compare both of them and see like why random forest will give you like I think it gives you like 4 to 5% higher accuracy.
Yeah. Okay.
So I think that will be a good comparison tool between a decision tree and what a random forest does. The main thing which you have to import is the sklearn ensemble method from random forest classifier. So if you have one of your old machine learning algorithms, just replace the algorithm as random forest classifier. You'll get that from sklearn model. Sorry, you'll get that from sklearn that ensemble method. So sklearn has certain ensemble methods. You can from that ensemble method you can actually create get a random forest classifier. If you have the decision tree also, then run them side by side and you can see that like what random forest classifier actually gives you more. I'll give you guys like 5 minutes. I mean, again, so don't rewrite this code. Just go to your old code where you have, or you can copy paste that code from your decision trees, and then just replace this algorithm as the random forest classifier, and you can train and predict it, and you can see how by dividing them into like further classes and stuff further. So basically you can change the number of features you want to select. You can change them. So this is like the default method which I've used, but you can actually, if you go into the random forest classifier example, you can actually go and change how many multiple classifiers do you want, how many how many observations you want to take and stuff like that. So this is just a default one which I've run. Let me run this. So my accuracy on the training data I'm getting is around like 70%, which I don't recall like for decision trees how much I got, but I think it was definitely less than 65% was what I recall getting for decision trees. So by using this, so it's around 70% every single time you run. So it actually improved the result accuracy by 6%. That's one of the, so on an average, it's around like 72%. Whereas on an average, decision tree was around 65 or some 60, remember somewhere in the 60 ballpark range. So like with the current example only which you have, you can then see like how by doing bagging, by creating this number of different classifiers and then taking an on like voting mechanism from each classifier, we can improve the individual results further. So first step is to decide on uh, which algorithm to use. So we have used decision trees. So in decision trees, if you want to actually improve the things further, the main thing which we are trying to avoid is the high bias which is coming from the data. For that, we actually divide the data into n segments, and then we run for each segment we run a decision tree which we can vary. But in this case, we won't do pruning or anything. We will basically run it such that like that. It's you need not worry about overfitting each individual decision tree in this case. What is the accuracy you guys are getting?
Just 2 more minutes.
Yeah. Deepika, are you able to run?
I just ran into some debugging issues, but
Oh, okay.
just
Okay.
if others are done, I think you can continue.
Yeah. So I think anyway, so it's pretty straightforward. Good. So the reason I wanted to run and show you this is like when you run this, right? Every time you run somewhere, my accuracy is somewhere around like, you can see that it is somewhere around 70% every time I run. So whereas when decision trees, we actually got a maximum accuracy around 64%. But using the bagging method, we actually improved that further. So one example of the bagging techniques which we did is basically the decision tree, is random forest. So in random forest, there is one thing which we need to observe is like, as the bag decision trees are constructed, we can calculate how much error the function, how much error drop is available at each point. So like again, like for each of the random forest, when we build a decision tree, we still use the Gini score to build it, but then you can see that the error drop which happens at each level is definitely higher. Obviously, the error before was 35%, and now it is gone down to like 30%. So these error drops can be averaged across all decision trees, and output provided is an estimate of like importance of each variable. So what that means is basically for each decision tree, when we are actually getting the error, since the output is basically an average of all the classification results, right? So it basically the errors tend to drop more, and that's one thing which I wanted to show you through running this thing is like, if you run it like n number of times, which you can consistently see that the results are around the 70 to 73% range. And then whereas if you used one decision tree on the same data, the results weren't that high. So that's one of the reasons why we do this bagging technique. The next technique which I wanted to do is boosting. So boosting is a slightly different approach. In boosting, actually, before I go into boosting, I actually want to show you like how. Let's talk about Ada Boost first. So in Ada Boost, what happens is, let's say you have a data and you have two classes. Let's say you have says class 1. There are two classes here. Mostly class 1 and class 2 are like this. So the pluses indicate class 1, and the negative signs indicate class 2. So let's say we have one algorithm which actually draws a decision boundary for these two classes. So this is boosting. So in boosting, what we do is, it is still an approach where we do iteration of it. We won't stop after one result, but then what we do is we take weak classifiers and boost the results. By that, what I mean is, let's say if this is our initial set of observations. Plus belongs to one class and negatives belong to another class. So let's say if we come up with one decision boundary which is like this. In this case, or maybe let me draw something better. So maybe if we come up with one decision boundary which is like this. In this case, most of the data is correctly classified, right? So you have a lot of plus points here and then a lot of minus points here. But then there are 2 points here. So these are the points which actually are misclassified, right? So what boosting does is, or specifically adaptive boosting does is, it's called Ada Boost. It actually, instead of classifying, one such, instead of using one classifier of this sort, what it does is it gives weightages to each of the misclassified features. So in the next case, what happens is your data set looks like this.
So though you have these features, the same features which are plus, 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 your negative ones have more weights now, or the ones which have been misclassified. So this will still be the same, but then it puts more weightage to the ones which have negative, which have been misclassified by the first classification. So this is your first classification, right? In the first classification, you get this results, and then you see what are the features which are getting contributed mainly from the error is contributing from which misclassified observation. Anything which has this misclassified observation, anything which has this misclassified observations, we give more weightage to it. So when you give it more weightage, the second time you're boosting the features which actually have been misclassified. You're applying a boost to them. So when you apply a boost to it by giving additional weights to them, next time you actually ask the classifier to classify it, it'll ensure that these are classified correctly. So what it'll do is it'll probably try to draw a decision boundary which is kind of like this. Now it will say that these ones I'll classify in one manner, and these ones, sorry, maybe this is the same thing. It'll probably try to classify them more closer to, let's say, we'll try to classify these correctly. So what we'll try to do is maybe draw a decision boundary which kind of looks like this. Though it has one this thing, now it'll, because two of them have higher weightage, it has classified these two correctly. In the next iteration, what you do is you will give all these other things higher weightage. So when these things have higher weightage, the next classifier will try to classify. So it adapts every single time you classify one set of classes, right? So in the first case, what happened is it tried to classify correctly, but then it got some misclassifications. So you added some weightage to these observations. Now, when you have these weightage to these observations, now the next time when you try to classify, it will ensure that these things are classified in the correct manner. These three things. I mean, this diagram is not that accurate, but then it will try to classify it in a proper manner, where which one the ones which you added weightages to. The next time, then again, the third iteration, what happens is everything which are misclassified in this, it will again try to add weightage to that and classify it further. So now what happens is you have classifier 1, classifier 2, classifier 3. So the output is again a combination of these classifiers. So what it does is, let's say if this has error, let's say this error is 30%. In this case, the error is maybe, let's say, 20%. When it tries, because in this case, it's only trying to classify the ones which have higher weightage, right? The third time when you actually get it, it'll probably get an error which is maybe, let's say, 33%. It'll still get the error from this misclassified ones, but it'll try to classify the ones which have more weightage. So now the first one has 20, the third one has 33%. The way you combine them is by the combination of these individual classifiers is inverse ratio of their errors. So that means that if this has 30% error, then you give it a weight 1 by 30 times the classifier 1 plus 1 by 20 times classifier 2 plus 1 by 33 times classifier 3. So this will be your final output. So this process is basically called boosting. So in boosting, what happens is you basically take one particular classifier, you try to classify it. Whatever ones have been classified wrongly, you give it additional weight. So you increase the weightage for the ones which have been misclassified correctly. The second time when it does, it tries to classify these things properly, and it might still encounter into some errors, right? Because it only relies on the fact that these things are classified correctly. And then the next time when it tries to classify it one step further, it again becomes the fact that it'll try to classify these ones properly, because these are the ones which are misclassified in the second time. So the second time, these are the ones which are misclassified. So then it creates another classifier which tries to classify these things. So ultimately, when we combine each of these classifiers, we try to give it a weightage which is basically inverse of the error percentage, because you want to actually have a classifier which has the least error. You want to give it more weightage to that, right? So it does an inverse combination of each of the Adabus classifiers. So this technique is called boosting. So in boosting, what happens is you first classify the algorithm, get all the ones which have been misclassified, and then put more weightage to the ones which have been misclassified. And once they've been misclassified, once they have higher weightage, the second time when the classifier runs, it tries to give it higher weight to the ones which basically have been misclassified, and then it proceeds further. So you basically do that for like 3, or depending on, that's again a hyperparameter, how many times you want to run the AdaBoost. Like you run it for 5 times. So the first time, second time, third time, fourth time, fifth time. So you run it like 5 to 6 times, and then and then the output will be basically uh, the output of each individual classifier. The weight will be the of uh, inverse order of the error percentage. So that is basically what boosting does. So boosting basically takes the misclassified outputs, gives them more weightage, and then tries to create a classifier which classifies these things correctly. Is any questions on like what boosting does? Is this thing clear? First of all, like adding weights to these things. Questions on boosting?
So like, what does the output of the boosting tell you, and like, what would you do with it then? Like, what would the next steps be?
So the next step, okay, this is a classification problem, right? So you actually have so this is classification. So classification is basically, you have 2 data sets. One is basically data set 1. The other one is the data set 2. The output of the boosting is basically going to improve the accuracy of your decision boundary. So here I'm actually having one decision boundary, which is like this. And then in this decision boundary, it has classified this correctly, because all the pluses are on one side and the negatives are on one side. But there are certain ones which actually are still misclassified. Like for example, there's a plus here and there are 2 negative signs on the other side. So the second iteration, you are saying to the algorithm that, hey, I don't care if you misclassify other points. I want to actually classify the ones which you have classified wrongly correctly. So if these have a weightage of 1, this will have a weightage of 2. So these ones will have higher weightage. Now, the second time when the algorithm runs, it takes care that the ones which it has misclassified in the last round, it will classify them correctly. But while doing that, it might again misclassify some other points also, right? So that will be the error the second time. So the third iteration, you will say that, hey, now in this case, you have actually misclassified these things. So put more weightages onto these things, which have been misclassified. The third iteration, what happens, it will try to classify that. So the output, what we are trying to optimize here, is a combination of all of them in the inverse order of their error percentage. So basically, the thing which we are trying to optimize is, we are trying to tell the algorithm that finally, when you come up with a decision boundary, so let me clear the drawing. So ultimately, at the end of it, so when you have like as having plus 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 minus 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 plus plus, it'll come up with a complex boundary which is like this. It'll be like maybe something like this. Again, it won't be like super overfit into like the problem like here, but then it'll probably try to come up with an algorithm boundary which looks like, it might have a boundary like this, something like this.
So then, like after applying the boosting, then the decision boundary is now optimized. So then, whenever you do like the test data, it'll classify it better, essentially, right?
It'll try to classify it better, because instead of so what you're doing is basically you're trying to add values to the ones which actually have been misclassified, and then you're trying to create. So again, this is also a combination of n classifiers. So both bagging and boosting are in the same lecture, because both, the difference between bagging and boosting is bagging also has n classifiers. The criteria for this is basically the fact that you divide the data set into multiple data sets and run it on different multiple algorithms. But in this case, whatever algorithm you're using, they are the standard algorithms, right? So they're basically the standard decision tree algorithms, which actually act as if the data is new, and then and then it takes some hyperparameters and trains them. The idea of boosting is also the same. The idea of boosting is also the same, but what in boosting, what we do is, instead of changing the data, we are changing the classifiers. Each classifier is adapting based on its previous classifier output. So the first classifier gives you some errors, right? The second classifier tries to rectify that. The third classifier tries to rectify this. So it basically, that's why it's called AdaBoost. In AdaBoost, what happens is it's trying to adaptively boost the ones which the first classifier has misclassified, creates another classifier. Third one adapts to the second one. Fourth one adapts to the third one, and so and so. So it basically goes in an adaptive fashion. So you basically first try to classify with the first algorithm, learn what from the mistakes what you made there, create a second classifier, create a third classifier, and then output is again a combination of these things. Even in this case, the output is a combination of these, right? So both bagging and boosting fall under the same bucket, where you're using multiple classifiers to get a better accuracy. But in the first case, your main goal is to reduce the variance. In the second case, and then get a higher accuracy. In this case, you're trying to actually get a better accuracy based on how your previous one has misclassified. The only thing in this case is we use weightages for the misclassified ones, such that the second one learns better from the first one, the third one learns better from the second one, and the fourth one learns better from the third one. And then
So I'm assuming that there's also like an option for how many boostings you go to, like the classifications, right?
No, again, like so both bagging and boosting don't have an optimal number. It's your time constraint is the main thing.
Okay.
So depending, if you have enough time, you can actually like train more and more and more methods.
But you should only go up till the value where you don't overfit the data.
Yeah, so generally you might not overfit, but you might converge to one particular value. So ideally you don't use it for more number of times. But the reason why we have bagging and boosting as two separate things is both of them, the principle underlying both of them is different. In case of boosting, the second classifier is based on the errors the first classifier has committed. The third one, so again, I'm not telling the second classifier is better than the first classifier, but the second classifier tries to capture what first classifier did not capture. So when you combine both classifier 1 and classifier 2 in their inverse order of their errors, this is a better classifier because it takes 30%. Like let's say if it has like an error of 30%, it takes 70% from here, and then it takes like maybe 60% of this thing. So the ones which this has misclassified, it gets added here. The ones what this has misclassified, it gets added from this third classifier. That's why boosting is also one of the important techniques. So these are the ones, once you have narrowed down which algorithms you have picked, so these are the ones which will help you improve your accuracy further and further. So that's why bagging and boosting are two techniques which will gain the additional 6%, additional 4%. So we actually saw algorithms where you get like 60% accuracy, but then how do you go from 60% to 70% is you use boosting or bagging. So this particular algorithm is called AdaBoost. AdaBoost is basically it's called adaptive boosting. Why is it called adaptive? It's because it's adapting to the previous classifier. When the first classifier has misclassified some things, we add weight to that particular classifier, and then we actually improve it in the second classifier and stuff like that. So again, you need not actually pick like what so there are default number of ones which you can pick. Like for example, in this case, I've kept the data set the same so that you can compare all of them with each other. So I've again used, in this case, in AdaBoost. So firstly, AdaBoost is again part of so if you see my code for AdaBoost, it's again a part of ensemble method. If you see here, it's again a part of the ensemble method of sklearn. So ensemble method one, which we have seen earlier, was random forest, which was used bagging, and then the AdaBoost classifier uses boosting, which actually learns from different classifiers and then do that. So in this case, I actually used an AdaBoost classifier. But then remember, it's not an algorithm in itself, right? AdaBoosting is basically not an algorithm. You have to pick one algorithm on which it has to act. Similarly, so both these techniques are not classification algorithms on themselves. Even in random forest, you are using decision tree as your standard this thing, but the combination, all these things are doing is combining these different classifiers into one and then giving you the output. Even in AdaBoost itself is not a classifier. AdaBoost only iterates over a given classifier. So firstly, in AdaBoost classifier, you have to give it, like I've given a decision tree classifier with depth 1, and then there is a algorithm called SAMME. So what that does is, using that algorithm, it adapts to so first it will use one decision classifier, creates another one which in which the first one has failed, has misclassified, creates another one in which the third one is better than the second one, or not better, but third one actually classifies the one which the second one has misclassified. So the first one, it has misclassified some of them, the second one takes care of that, but in that process the second one also can misclassify some of the points. The third one actually tries to classify them properly. So you have to pass in a basic classifier to it, and then it basically runs on those things. So you can see here, when I did AdaBoost, so let us see the results of which one is better. We did random forest and we are doing AdaBoost, right? So let us see. So you see, AdaBoost is also giving somewhat similar to like what random forest gives. Let me run it a couple of times. So AdaBoost is actually giving you like 73%, whereas that was around 70% average. So boosting is actually helping you gain better results. So the idea is this: like once you have one particular algorithm, the thing is you need to improve on that algorithm. You have to get very close results to like higher accuracy on the test data. So 74% is like really good. So 74% means 3/4 of the time your algorithm does really well. So generally, like in complex cases, in medical data especially, like if you're, so these will work as recommendation systems to your doctors, right? So when the doctor actually gets a new patient data, you might give him a warning saying that, hey, this person might be diabetic, or this person may have liver cancer. So 75% of the time, if it is suggesting the right thing to the doctor, then it is a really useful algorithm. So it's pretty much that. So what it does is, so none of these actually tell you like what goes on in the background, but that's why the coding aspect of it is just change of one line. So if you have the previous code, just change it to AdaBoost classifier and you will see the improvement in the accuracy. So anyway, so this is what AdaBoost does. So any questions on AdaBoost? So here I see I can pass it the number of estimators. So I've iterated it 200 times. So first one, second one, third one, I've actually then combined 200 outputs of each individual classifier into one, and then I got an accuracy of like 74%. So let's just go through this. So the slides are basically telling the same thing about what like boosting does and stuff. So I'll just go through. So boosting is another ensemble method that creates a strong classifier from a number of weak classifiers. the combination, combine the predictions of each classifier. It uses either the average of them or it uses some kind of a higher vote. So what we have done and what AdaBoost does is it does a weighted average. The weights are the weights are in the reverse order of their error percentage. So the first classifier has some error. It will actually combine the result of that in the reverse order of their error percentage. So the lower the error, higher is the weightage given to that particular classifier. So one example is basically, let's say we are trying to classify if a given email is a spam email or not. So in this case, we'll use boosting. So we'll take simple classifiers first. So what we'll do is we'll take 1 week classifier. If the email has a single image, then it's a spam. Then another weak classifier is basically if the image is it's from a trusted domain, it's not a spam. So we take these small weak classifiers and then we train on them by so the first weak classifier output is given, and then the output of the first weak classifier is fed into the second weak classifier. But in the second weak classifier, we say that, hey, whatever the first one has classified wrongly, please pay more attention to that one. So then the second one actually trains on the one the first one has misclassified. Similarly, it basically adapts to the each classifier will adapt to what the previous one has misclassified. Is that clear? Any questions on what adaptive boosting does?
No, it's clear.
Deepika, any questions on this?
No questions.
So basically, these two things are important to get the accuracy. So we use decision trees, right? We use decision trees for Indian liver patients. We got 65% accuracy. How do we improve from 65% accuracy to like 75% accuracy? So these are the two techniques which generally machine learning people use to actually improve the accuracy further. So one method is the bagging method, and other method is the but both of them target different sections of the uh, different sections. Like the bagging method tries to improve the accuracy by removing the variance from each individual classifier. In this case, in adaptive boosting, what it does is it takes the first algorithm, it sees what has been misclassified, and then adds weights to the one which have been misclassified, and second one tries to get the ones which the first one failed. In that process, second one might also get less number of misclassifications. So the third one will actually improve on that. Fourth one will improve on that. So it basically, depending on the number of classifiers you have, the adaptive boosting actually works. So let's take a small example, right? So assume that we are working on a two-class pattern recognition problem, and we are given for a large given sample. So we want to combine, we want to put together a combination of 11 classifiers extracted from the pool. So each of the pattern is given to each of the individual 11 classifiers, and then the final decision is a weighted sum of the thing. How do we decide these weights? These weights are decided on the reverse order of their error percentage. The second one actually adapts from the first one's output. We give certain weight to that, and then the higher the weight for the misclassified ones from the first output, the second one works on it, the third one works on the next one, and then finally we combine all of them into one such uh, classification output. The constraints are basically the weights we assign for the opinion of each classifier. The arrangement of this is a linear combination. So classifiers are given as an input to the AdaBoost technique. So in each of the case, the first classifier learns from the second classifier, which learns from the third classifier. So the first one which it fails to predict, the second one works on it. Second one which it fails to predict, the third one works on it. And ultimately we do a linear classification of this thing. So each of them are called decision stumps. So they generally use the word decision stumps more precise. So the first classifier is called first decision stump. The second classifier is called second decision stump. So generally, error boosting is used more in classification and regression problems, because if we, how are we getting the input for the second one, right? Because we are getting the misclassified outputs from the first one and we're feeding it to the second one. So generally, error boost is useful for classification problems, where the first classification, if it is misclassified, then the second one gets to it, and then if that is misclassified, then the third one gets to it, and the final output is basically given as a combination of each individual classifiers. So this is just an example of what we just saw, how each of them are misclassified. Let's say we have 3 training instances, we have weights, and each time the weight is updated based on the error. So if the error kind of decreases for the first one, then you actually take the weighted combination of the errors to get to the second one. So this is the math behind it, like how the errors are calculated and at every stage. So you take an exponential component of the error, and then so all this happens in the background of the error boost algorithm. So at every layer, like in this case I've told you, right? Like if I go back to the whiteboard, so let me just clear this drawings. So you have the first classifier, right? The first classifier maybe has an error of, let's say, 30%. So it classified 70% correctly, 30% are wrong. The second classifier will actually take these 30% of them and try to classify them correctly. So more weight is given to that. But this can also have an error of, maybe it can have a higher error. Okay, here's a question. Why do you think the second classifier will have a higher error? It is actually learning from this, right? But it can have a higher error than the first one. Why?
Because while it's trying to correct the first, correct the mistakes from the first one, it's probably making more mistakes in classifying the others.
Exactly. So this error, I mean, it is not adapting to basically improve the accuracy. It is adapting to rectify the errors of the first classifier. So you're actually,
This is kind of like solving a Rubik's Cube, because like in a Rubik's Cube, to fix one side, sometimes you need to mess up the other side, but eventually they'll all get fixed.
yes, but in this case, it's exactly like that. So in the first case, half of the, like it actually has a very good accuracy, 70%, right? But then it actually classified some of them, those 30% of them misclassified, misclassified. So the weights which we give to them, so that is what these weights are. We generally give. So I think a much better thing, which is a MATLAB code for learning AdaBoost, because in MATLAB code they'll actually tell you how the weights are changed. So they have exponential weights. That's what I've actually have in this slide here. Is like, how are these weights? So now, instead of giving, so earlier we used to give the features, right? We'll give just the feature 1, feature 2, feature 3 to the algorithm. In this case, what we'll do is we'll give some weight times feature 1, some weight times feature 2, and some weight times feature 3. These weights are updated based on this misclassification. So here it has misclassified these. So the only input to the second one is saying that, hey, give more importance to the ones which this has misclassified. So in that process, it will, though it is having a higher error, but it will try to classify the ones which the first one has misclassified. So that's why you see that it might increase in error. But then the trick lies in how you combine these results. So you have like 3 classifiers. Now it says that the first one is 30% error. So you will do 1 by inverse of that. So it is inverse of, like, so this one has higher error. So you'll take less percentage of that. So let's say you take 0.67% of the, I mean, obviously you normalize that. So you take 0.67 of the second classifier, because that's the accuracy, 0.7 of the first classifier, plus, let's say the third one has 22% error. So you take 0.78 of the third classifier divided by 0.7 plus 0.67 plus 0.78. So this is the weighted error, because this has to be, obviously when you add them, it has to come down to 1, right? So this is the weighted error, you classify them. So this is the output of your final adder boost classifier. So this is your spot on. So this can have a higher error, but then the reason for that is not because, oh, you might think that, oh, if it actually is adapting from this, why is this error not going down? Because we are not trying to optimize the error. We are trying to say, hey, classifier 2, some reason classifier 1 couldn't classify some of them. You only focus on the ones which it did not classify. And how do you say that? Is by passing these weights. So you update the weights every single time. Every single time this misclassifies, you update the weights for it, and then you pass it to the second one, and then you update the weight for it, you pass it to the third one, and then the combination of that is basically what you will use for your final output. So is that clear of how the adder boost thing works? Because if you're using Python packages, you generally will not see the math behind it and stuff like that. Actually, a MATLAB package does a really good job of showing how these things generally differ. But then the reason is because you generally don't care, right? You just pass in like one number. So you can actually change those. If you look at the Adabus classifier documentation, it'll tell you like, hey, first one is like, but again, remember, Adaboost and random forest. I mean, random forest actually they are not the algorithms. The algorithm is still a decision tree. These things are only combining different outputs to one. So that's why it's called boosting or bagging. They are not algorithms in themselves. So you first thing you need to do is to pass in the main algorithm, in this case, which is a decision tree. Second thing which you need to do is to pass in number of times you want to use the output of that, and then optimize it further. And then finally you get, so now you see that when you do adder boost, your accuracy results have been consistently around like, oh, here I didn't do the random state, so that's why it is the same. But if I actually change my random state to true, is 100, then basically, so in this case I have actually done 7. So what this random state does, it takes 7 outputs and then gives you the final one. So anyway, but your accuracy is way better than what if you just use decision tree, this is much better. So that is what adder boost does. But one thing in adder boost, which is basically so these are additional slides for you, like if you want to understand how each stage the weights are updated and stuff, you can go through them. But I don't really think like you would want to care, because the algorithm itself will take care of the training process. But once you complete it, you actually create a more powerful algorithm from the set of weak learners, because first one learned something weak, but the second one actually improved on the ones which had failed. Third one improves on the one which the first one has failed and stuff.
Now, can I ask a question?
Yeah, sure.
So I have actually 2 questions. So is AdaBoost also a type of ensemble method?
It is, right, because it is combining. So what is ensemble? Ensemble
A
means
technique that combines predictions from
anything which
multiple.
combines predictions from multiple classifiers is called ensemble. So
Okay.
ensemble. So even in case of these problems, you have something called as ensemble voting. What ensemble voting means is like you have multiple of them, and then you get outputs of each of them. Either you use voting method to combine them, either you use weighted average. Adaboost actually uses weighted average to combine them. Whereas this thing might use mode, like if you're using it for random forest, it might use mode to combine them. So different methods of combining, but anything which uses multiple classifier outputs is called an ensemble method.
Okay. And then my other question was, one second. Ensemble. Okay, and then my other question is kind of like just a clarification on both bagging and boosting, or specifically the random forest bagging and then the add boost. For the random forest, we can have multiple classifiers, right? So we can have something like the first time we run it, we want a decision tree with depth 3, then the second time with depth 2, and then the third time we want to do it with Genie index, something like that. So we have different outputs for those 3.
Yeah.
But with AdaBoost, can we choose different classifiers, or in every time we run it, does it have to be the same classifier?
No, you can use different classifiers. So for example, like this is the example I was giving, right? So in this case, like the example for one of the examples for AdaBoost was the email, the spam classification.
Mm-hmm.
So here you say that it's a spam or not. So the first classifier you take is if the email has a single image, then it is spam.
Mm.
And the second classifier you take is if this email is from a trusted domain, it is not a spam.
Mm.
So if it's not from a trusted domain, then it is a spam. So you use the first classifier, which is basically is the image spam or not. So basically, I don't know why is it erasing. Let me just do this. So basically, you take one email and then say spam or not. So you say yes, it's spam, and no, it's not spam. So then the output of this. So here you might, let's say you're classifying 100 emails, right? Here you have 70 and you have 30. Let's say if things which have like I'm sorry, this is single image or not, right? So if it has single image, we say it is a spam. If it does not have single image, then it's not a spam. So maybe it has classified 30 of them correctly. Now what you do is these 30 ones, you give it additional weightage and then use the second classifier. The second classifier says that trusted domain or not. So in this trusted domain, it'll ensure that these 30 ones are actually classified correctly. At least out of 30, you'll have 28 of these things, plus it might classify some of this also, like 50 of them, and then it'll have some other errors. So each one need not be the same classifiers. This is basically a bunch of different classifiers, and then you will basically use it. If you don't have any classifier, you can use the same one also.
Okay, can you show us in the code where we would specify the different classifiers? Because I couldn't see.
Yeah, it is not because this one I've just used the same one. So in this
So
case,
like how would you want to specify the multiple classifiers?
I think if you just,
Because if you're like running this, AdaBoost, for example, like 20 times, would you have to say in each like nth iteration, I want to run this specific classifier, or how would you do that? Like the first time I want to run depth2, the second time I want to run with Genie index, third time I want to run with this.
so there is you can basically change them, and if you look at the documentation of the AdaBoost, typing,
We can't see your screen.
you can't see. 1 second. One second. This is. Let me just cancel this. Just 1 second.
Yeah.
This, I think this is just stuck there. So can you see my screen?
Yeah.
So here you have the AdaBoost classifier.
Mm-hmm.
So this is the action. So all these things have their documentation. So sklearn's ensemble method has AdaBoost classifier. Here, basically you have a base classifier. If you don't specify a base classifier, it's not good. The base classifier is what I've actually used in my cases, which is basically like the decision tree. So there, in this case, if you actually look at some advanced parameters here, estimators, you can collect a list of. So these are the additional parameters which you can. So it'll come under the estimator class.
Mm.
So you can provide a collection of the sub-fitted estimators, and then you can just pass it in the attributes here. So if you want to, so this is a simple implementation which actually I've shown you. in this case. But if you want to provide more attributes to it, like in the advanced this thing, you can actually go and say that, hey, I don't want to use one of them, but I can provide a list of classifiers in your attributes.
So then it would create, if I provided,
In the
two.
order of
You have to provide them in the order in which you want to know which one is first and which one is second.
So if I only provided 2 and I was running this at a boost 100 times, it would use both classifiers 50 times?
Yes.
Okay.
So yeah, so that's why, I mean, I had like the basic implementation where I've used only one. So this is the default implementation, right? So the base estimator is I've used the base estimator as the decision tree. If it is none, it'll take the base estimator as this thing. But you can actually then use different estimators and stuff like that.
Okay.
So like if you just actually try, I mean, if you have this thing, just change these things and see right now, or just first run this is again. So from the last from this particular case, right, from the random forest, you just have to change one thing here. All you need to change here is basically this thing. All you have to change here is basically this line here. So it's again the same. You create the model, you fit the model, you predict the model. So it's just one line change. Actually, if you've written the previous code, just change this line and see. If you want, you can just use the attributes again. That will provide you a list of estimators. Like instead of using one default, like for the spam classification problem, you can create submodels. So that's a little advanced thing, right? You can create submodels as to which ones you want to use, and then you can pass that list in here. So quickly change this and see how if your output is actually improving. If your output is better than the So are you guys able to write this? Just quickly change this line and see what your output is. I'll just be back.
Are you guys able to write it? So I would suggest you actually make one template like this, because every time it's just all we are doing is just changing one or two of them. Like from the ensemble method, we're adding one line, and then we're just adding like just changing the model we fit here. As you can see, in case of like random forest, we just had this thing, right? Like random classifier. In this add a boost, we are just, so it's pretty much the same model which we have been following. That's why writing the code for this should be relatively straightforward, but understanding what it does is a little bit more important. So I'm hoping all of you have this template ready, right? Like for Deepika, is your thing from random forest working?
Yeah, it is working. Fine.
Okay, then how much is the accuracy you got from random forest?
Yeah, 1 second. So I got 79% accuracy.
Oh, really? Not training, testing.
The testing one, right?
Yeah, testing. You got 79. What is the split you did? 0.3?
So I did 0.3. I tried 0.3. I tried 0.4. I tried a list of things.
Okay, now the same thing here. You just have to change for Ada Boost. You have to change this line. Everything else remains the same.
Okay.
You just change this line, and then that's your new algorithm.
Okay.
So if you try a boost, so until now I've only taught like things which are new algorithms and stuff. So these boosting and bagging are things which you use to get that extra mile. Like once you have an algorithm, to remove the bias from the data, to remove to use, if you have like, mainly you can use it also for when you have like weak classifier algorithms, you can actually use it to combine them and create a much stronger classification algorithm. So as far as I know, I don't know, even in neural networks we did not get this much, right? Let me check. Did we get this much accuracy in neural network? Let's see, test cancer data. Oh no, I want to use it for the same thing. So let me see how much is accuracy I got for ANN. Oh, this is the TensorFlow error. Okay. I'm pretty sure like the AdaBoost is the best accuracy I've got so far, which is like 73% or 74%. But you can do further things in AdaBoost by changing these classifiers in the middle, and then as I think Meher has asked, right, you can give it a bunch of classifiers also from your list of estimators, and but then you need to use, so every time when you're using these, right, go check out the documentation for these individual algorithms for AdaBoost or like all these sklearn libraries. Check out what the individual algorithms are. So anyways, when you guys are doing that, I think we have 30 minutes left. There's one more boosting algorithm called gradient boosting. It's actually called XGBoost. Again, from coding perspective, it's not much different. All you need to do is change that algorithm and say XGBoost classifier. So this is basically another algorithm. One limitation of AdaBoost is basically that it is only used for classification purposes, right? Because unless you have the errors from classification, you won't know what to give it the second model. So you basically have 3 training instances. You actually give the classification results out. But this next algorithm which we are doing, it's called gradient descent boosting. So this is generally the main use of that is for regression purposes. Like when you want to improve your regression data, so you try to basically use gradient boosting. So what do I mean by that? So again, we have seen like what regression is in like quite a few times in our lectures, right? So let's say if we have, let me just give a brief overview of what gradient descent boosting does. So gradient descent descent. So what gradient descent boosting does is basically it tries to fit the data, fit a structure to the given data, but it uses this concept of gradient descent to fit the data. So what it does is basically, let's say if you have some data which is like this, let's say it is like this is your data, right, which is basically, and let's say if we have one classifier which is like this, or this is the first fit of the data. So this is not the best fit. So again, in gradient descent also, these are boosting algorithms. Boosting algorithms always work on the fact that you have error from the first one. They boost that error, and then you use it for the second one. So that's what, whenever you see the word boost, it means that they boost
errors from the first algorithm to the next algorithm. So that's why they're called boosting. So let's say if you have data which is like this. So again, this is a regression for regressions. So AdaBoost is used for classification. Gradient descent is used for regressions mainly. You can use it for classification also, but its main purpose is using for regression, because as we have seen, the line which we fit and everything is for regression, right? In when we learned gradient descent algorithm. So let's say if you have the data which is like this. So if the data is like this, so as you can clearly see, the error is really large, right? Because initially here it is actually fine, but as the data improves here, it is basically a straight line. So what they do is they try to create a model for the error. The error, if you look at it, it will be like this. Because the error here is larger, error here is smaller. So the error is smaller here. And then after this point, the error becomes large. So this is the first model which fits something like this. The second model is developed on the error. So you have the error. You do so this is basically a linear regression or a regression algorithm on error on the actual data, right? The first step is the data. Second step is the error of the data. Error from the fit. This is the error from the fit. They try to actually use the same regression model to fit the error. So the error will also from each of the points will be like this. So they'll actually try to model one algorithm which will fit the error. So error is like this, so it'll fit a line for the error. So then how is this line fit for the error? It's using gradient descent. So what they do is they take the way they update the weights, or the way they update the parameters for the first one is by taking the old parameters times some learning rate times this error divided by that parameter. So this is like gradient descent algorithm. Like we have seen this like quite a few number of times. So visually, if you see, there's one model which is fit for the error. There's one model which is fit for this thing. And then there'll be again error from this. So they'll fit another model for the error from this thing. So if that model actually has some error, they'll fit another model. So ultimately they'll combine all these models together. So when you combine all these things together, you will have your final regression graph will look something like this. Because you see, it is trying to boost in this section. It is saying, hey, go up. So you'll try to go do this and it'll try to go up here. So this is a much better fit, right? If you look at the data is like this. Initially you fit something which is like this, but after taking into this error and you combine this into your original fit, it's saying here don't add much, but after this point add this much section. So it is going to like do this. And now this is a much better model than your original model. So that is basically gradient descent boosting. Gradient descent boosting is mainly used for regression. The way they try to actually boost or the shape of this thing, shape of your line is basically by saying that looking at the error, you add that particular thing to your current line fit, and then from the fit which you get from the error, you again add it back to your original one. So ultimately, and then this will have lesser error. You'll have some fit from here. You'll add this. All of these are again combined together into one classifier. So this is also boosting. This is also an ensemble method, because your next model, they're all different models and you're combining the models. The whole point of ensemble is basically combining the outputs of different models into one. In case of gradient descent, the way they combine that is by using the error function. So first time when you do a fit, you get some error, you fit a line to that error, and then you fit a line to the next error, you fit a line to the next error, and then you combine all of them into one of them. So that's how you will basically, the gradient descent algorithm works. So every time you have a fit, you try to find out its error, you fit the error, you combine that new fit into this one. Again, you take the error from this, you combine that fit into this one, and ultimately it will boil down to a much smoother fit. So you take like a weakest fit, but then
the more weaker your initial fit is, the higher your error function is, right? So this fit will actually compensate for the weakness in the first one. So that's why it's called boosting again. So is this clear? Like we'll look into like how like the slides on like boosting, but this is pretty much what it does. So gradient descent is basically the whole formula of gradient descent is this. We've seen so far that it is actually the old one times some learning rate, and depending on the error, you're updating the parameters, right? Here also it's doing the same thing. You're taking the first one, you're taking its error. Depending on the error, you're going to update what the uh, original thing is. That's how you get a better fit to that model. So let us. Okay. So basically in boosting, these models are built sequentially. Each successive model weights are adjusted based on the learning from the previous model. Gradient boosting works on reducing the errors sequentially. Gradient boosting is trying to develop a new sequence model for hard to fit data. So when you have some data which is hard to fit, depending on the previous error of what has your previous model has given, it'll try to fit that data into this thing. So what is the error term they use? They use the difference between the observation and the predicted one. The residual is the gradient of the observation error contribution from one of the so it's called root mean square error, RMSE. RMSE means that for each of the individual points, you calculate its root mean square error. So you basically take the current observation and predicted observation, and you calculate the error. So the whole sum of all of them, so it is basically root of mean of the squared errors. So the squared error for each individual data, you take its mean and take its root. So that is basically the error on which they'll optimize on. So for every time you have a fit, you're going to fit another model based for the error, and then combine that model into the first one. So gradient boosting involves three elements. One is the loss function, which is to be optimized. One weak learner, which makes the first predictions, and then an additive model to the weak learner to minimize the loss function. The first one basically tries to fit the data. That's a weak fit. The additive model is the one which actually tries to minimize the loss function. Loss function is nothing but the error here. So the loss function is from this slide. If you look at it, it is the root mean squared error for that particular model. So loss function is used depends on the type of problem we want to solve. If it must be differentiable, because gradient descent actually works on the differential of that error function, right? For example, in regression, you may use like squared error, but in classification, you use logarithmic loss. So depending on what kind of problem you want to solve, that's how you define your loss function as. One benefit of gradient boosting framework is that the new boosting algorithm does not have to be derived for each loss function which may be used. So basically the takeaway point is you first create a loss function which is differentiable. And then if you are doing regression, you may use squared error. If you are using classification, you may use logarithmic loss or some other loss function. But you need not worry about that. Like the algorithm in the XGBoost classifier will take care of that. But if you want to specify different loss functions, again, you can look at the documentation for this in the sklearn library, and it will tell you like what kind of loss functions you can use and stuff like that. So weak learners, right? So basically you can take decision trees. So this is the classification problem. Decision trees can be used as weak learners in gradient descent. Specifically in regression trees are used where the output real values are for split nodes and whose output can be added together, allowing the subsequent model outputs to be added and the correct residual in the prediction. So this is also greedy algorithm, in which case what it tries to do is, so what is a greedy algorithm, right? A greedy algorithm is the one which actually tries to minimize a loss function because it's greedy, right? So it doesn't want losses. So it tries to minimize a loss function, and every iteration, every classifier it has is trying to actually model or such that the loss function is reduced. So in this case, when I showed you this, right? So first case when I drew the thing, it was just this. So it had a loss function, which is the error term. So in the error term, when you actually have the error, you try to fit an error model, and so this is basically added back to this thing. So it is trying to minimize the loss function. So when the next time when you actually come here, your model is changed. It takes the current model, and then it takes the model which you get from the error, and it adds it to this thing. So that's how you actually try to model this. So let us go back to. So this is another boosting algorithm which basically is used, but most of the times, like AdaBoost is like mostly used. I've seen very rare cases where XGBoost perform better than AdaBoost, but again, regression problems you basically have. In regression problems, you basically use a gradient descent model, not for classification problems. So in additive model, the additive model is nothing but which is basically developed on the error, right? So the trees are added one at a time, and the existing trees in the model are not changed. A gradient descent procedure is used to optimize the loss when adding the trees. So traditionally, gradient descent is used to compute a set of parameters such as coefficients in the regression coefficients or weights in the neural network, and after calculating the loss, the weights are updated. So we've seen this when we did neural networks, right? How the weights are updated. So it's typically the regression equation has the same thing. So you take the weight, you calculate the error, you differentiate it, and you update the weight. So this is the additive model, in which case you're modeling the error here and then adding it back to this. So the type of things you can actually change in your bagging algorithms are like the tree depth, number of trees, number of nodes, or number of leaves, number of observations you want to split. So these are the different ones you can, if you're using like a decision tree as your base algorithm, these are the different things you can change in that particular tree. So each classifier can have different set of these things to make it a new classifier. And then the predictions of each tree are added together in a sequential manner, and then the prediction of each tree is added in a sequential manner, and similar to this thing, right? Like, so even in this case when I showed you, you add this thing in a sequential manner. First you calculate, you fit a model, you get the error here, and then you add this to this, and then this error you again model it again, you add this to this. So sequentially you add each of them together, and then that's how you basically end up by getting another classifier model based on each individual classifiers. So from coding perspective, this is again simple. You can actually give it again a list of uh, so in this case it's basically not a list because it actually works on the error function, right? But you can give it a list of in case of regression you can say linear fit, polynomial fit, or some other fit. So depending on the kind of fits you want to give, you can give in this thing, but everything will be added in the other, in case of AdaBoost, it is actually doing it for the misclassified outputs of the first classifier. In this case, it is doing it on the error functions of the first classifier. So that's the only difference between XGBoost and AdaBoost. So the way you can actually train this or like move this is basically by calling the XGB classifier in the sklearn library. It's the same thing. So if you have written that code, then you can actually change this also and see. But according to my understanding, I kind of think AdaBoost was the better performing one. Let's see. Oh, this is getting 74%. Okay. Okay, this is better than it's like 1% better than the AdaBoost classifier. So you can see that. So one thing I think you might not. Oh, I forgot to mention one thing. Here I have to change the input data. So for some reason, so I tried to use read CSV. It wasn't working well. So I went back to using load text, because for some reason, for classifying, for giving the input to this, it was not working properly. So I used np.loadText. Everywhere else we have used pd.readcsv, right? And when I used np.loadText, I actually had to delete the column because it was reading the whole text. So I created new data sets here. So if you look at my uh, these outputs, I created one more data set from the cleanse data, which is nothing but it's just the same thing, but I removed the column names. So the first row has been deleted here. So it's the same thing, but I've removed the column names from the top. So if you're actually giving it into the, oops, so if you're giving an input into your XGBoost algorithm, you have to basically remove the first column and then give it into this. And the thing I've used here is basically called as uh, I've used np.loadText function instead of using pd.readcsv. I've used np.loadText to do that. I think that's the same I've used for AdaBoost and this thing and XGBoost. So if you're were anyone of you able to run the AdaBoost algorithm? I forgot to mention this. This is the one change I did here, is to use np.loadText. So I used NumPy array, NumPy data structure to do the load test for that, and I've read the CSV file from the text file. So if you're actually trying to use an XGB classifier or AdaBoost classifier, please note that I've actually used numpy.loadText instead of using pd.readcsv. I was getting some error when I did pd.readcsv for this. I used load text, but in this I actually created another CSV file which from which I've deleted the name of the columns.
Okay, I was running into errors because I used load text, so I just changed back to read CSV.
Okay, no, you can use load text, but the only problem with load text is when you do load text, you will it won't be able to convert the column names. It won't be able to convert the string into a value. So the
Okay.
only thing which you need to do in that case is create another CSV file. Which you take the original CSV file and delete the column name.
Okay.
So you have the
I'll try
column
that.
name here. Right. So you take the column name here. So just this thing. You just take the column name and say just delete this, and then save it as another CSV file, and now you can use np.loadText. I don't know, maybe if you guys can figure out why read CSV wasn't working. I tried using read CSV. That's why you see that I have commented it out here. I tried using read CSV, but for some reason I was running into some errors. So I just used load.txt to run into to basically use this and classify it further. But overall, like in general, right, like this is an additional thing. Like when you want to improve your results further, boosting and bagging are two techniques which you can use to gain like better results from your current training data model. So yeah, try this these two things and then see if your prediction accuracy is increase further. The other thing which I wanted to tell was we have three more classes left, right? And in these three classes, which I wanted to see, so one class I was thinking of doing naive-Bayes algorithm. So it's another algorithm which is used based on completely probability. But like I just want to know like how good does your probability like
Do you know what Bayes theorem is and stuff like that, or should I cover that as well? See, how many of you know what Bayes theorem is? Does anyone know what Bayes theorem is, or should we?
I have a rough idea about it.
So Bayes theorem is basically is the probability of A given B. So generally, when you have probability, like for example, what is the probability that it will rain given that tomorrow's forecast is cloudy? So A given B, that's like what Bayes theorem talks about. And there is a whole again classification algorithm based on the naive Bayes. So it's called the naive Bayes algorithm. So it uses the naive and the Bayes theorem together to use it for classification. So it's completely a probabilistic model. So I think it's interesting because there are a lot of applications for naive Bayes, especially in case where you have to, like weather predictions and stuff like that. So they're very, especially weather predictions, they use naive Bayes quite a few times in that. So there's naive Bayes algorithm, which is again a classification algorithm. So I was thinking on Wednesday we'll do naive Bayes, and then I'll give a break. So Sunday we have no class, but in this Sunday I want to like revise all the classification algorithms in Python, which we did. So finish assignments or finish all the assignments. And then on the next Wednesday class, we'll start with R. So we'll do introduction to R. We will cover like mainly like R functions, plotting, and uh, like loading modules. So from now on, we won't use Python. From next Wednesday, we'll just see how to actually start with the R functions and stuff. And then the next Sunday class is our last class. So I was thinking of we'll do linear regression and logistic regression. So, but both of this will be done in R. So we have a case study for this. So the case study is a standard case study where we have the data from a New York. There's a sales shop in New York. So New York bike rental place. So they actually have this data given a lot of parameters. So they have the data saying like the number of bikes they have, given weather, given like a bunch of other things like humidity, like how many people rent these bikes based on that, and then like a bunch of other parameters. And then they actually have a case study to, given some other conditions, can we predict how many bikes should they? So that's why it's a regression problem, right? So it's all the same kind of data, but given one quantity, can we predict how many bikes do they need to store for 1 week from now, 2 weeks from now, and stuff. So both these things will be done in R. So I think Meher, Satvik, you guys actually are in college right now, right? Do you guys, did they teach R in college?
Not
Only
in college. I'm in high school.
only I'm in.
Oh, do they teach you R?
Yeah, I mean they do, but like they're teaching it in statistics classes, but I haven't had the need to take those stats classes,
Okay.
so I haven't
Okay.
been using it. But I know that people who aren't really in computer science are using R right now. Like some pre-med kids are using it.
Yeah, so R is actually picking up. So next week we'll cover naive Bayes algorithm, which is basically another algorithm based on probabilities. So this will, I have to like teach a little bit of statistics, probability here. So probability mainly Bayes theorem, which is it's a very useful. If you learn probability and statistics, it's a very useful algorithm for solving a lot of other issues. So we'll cover naive Bayes with probability on Wednesday. But then after this on Sunday, I want to basically give a break so that you finish, like you revise everything, because that we have done a lot of algorithms in like a few weeks, and it's just sometimes overwhelming to like get and understand each of them. So because we have We did like neural networks, we did support vector machines, we did k-means, we did decision trees, we did adab boost, we did xgboost, we did random forest, we did like we did quite a few classification algorithms right now, and most of them in Python. So just finish wrapping up all the assignments, just get an understanding on Sunday to revise all of them. So on from next Wednesday, we'll start afresh. We'll start with R. We will see how to run R scripts. We'll use how to load R Studio, and we'll do some basic things in R, like loading data and then modules and how do we use modules. And using those modules, we'll do this. So understanding linear regression and logistic regression is very easy. We've already done kind of linear regression in gradient descent, right? So in gradient descent, that's pretty much what linear regression is: fitting a linear line through a bunch of data based on optimizing the error function. But then we will see that in a little bit more detail. But then we will see, instead of doing linear regression, what logistic regression. This is a little more interesting. Logistic regression class is a little bit more. So instead of fitting linear models, we can fit logistic models on categorical data and stuff like that. So so the theory of that will not take a long time, but we'll spend some time on the case study with the New York bike rental uh, thing using linear regression. So I guess like that. So that will actually conclude our course curriculum on like so unsupervised learning, supervised learning, regression, classification problems and stuff. Is that sound good, or should we actually, or should we cut down on any? Do you guys want to learn naive base, or should I actually start R on Wednesday? Because naive base is originally not part of our curriculum. I thought it'll be useful to learn, because all these ones are based on statistics, right? We have not done any algorithm based on probability. So this naive base is like a very widely used algorithm for weather predictions and stuff, like, because it's all probabilistic data. It's not statistical modeling. So it's all whether it'll rain tomorrow given this condition, whether it'll rain tomorrow, like it's all a probability based. It's a different type of algorithm. It's still a classification based algorithm. There's still training and everything, but it is based on like probability distributions. If not, then we can I can start with R. I can spend like a good 2 days in R, and then we can. So it's your guys' call. Like, what do you think? Like, you think you guys want to learn naive base, or
Yeah, I think it would be good because we haven't even seen any probability ones, right? So if we ever encounter a problem, then we need to use probability for them.
okay? Then we'll do naive base on Wednesday, and we'll we'll spend one whole day on R, like installing modules and stuff. And then logistic regression and linear regression can use these modules to show. R is like very simple language to learn, like it's very easy. It's not super complex. It's like MATLAB. If you learn, if you know how to use MATLAB, R is like very straightforward. Like it's exactly like MATLAB. So I don't know how many of you know how to use MATLAB, but all right then. Any questions on like today or like next week, what we want to do? Just remember one thing is like I mean you can use read CSV, but I don't know, I ran into some issue, but I used load text. So if you're using load text, create another CSV file by deleting the first row. So if you want to run this part of the code. So if there are no questions, then I think we'll stop today's class here. And then Wednesday we'll start with a completely new type of algorithm, which is based on probability and Bayes theorem. So I'll send this code and this thing immediately, but it's taking me like 1 or 2 days for the video because it's like 2 hours, right? So it's processing for a long time. So I'll send the videos hopefully by tomorrow or if not day after tomorrow. But I'll send the code immediately and then we can take it from there. So any questions from today's lecture or previous ones or anything which you want to discuss now, or else I think we'll stop the class now.
No questions.
Okay. Then I think, have a nice rest of your day and I'll see you guys on Wednesday then.
Okay. Yeah. Thanks, Sai. Thank you
Okay.
very much.
Thank you.
Thank you.
All right. Harun, Satvik, see you guys on Wednesday.
Yeah. Thank you.
All right. See you. Bye.